Welcome to numerical ship and offshore hydrodynamics. Today is the lecture 50. Today again we are going to discuss about the nonlinear time domain panel method. Today's discussion is, if you remember, that today we are going to discuss the algorithm where we can pick the exact weighted surface, and this is the keyword that you have to use to get this lecture. Okay. So, let us start. Now, when I say that exact free surface, we discussed a lot, we mean that exact wave incident wave, linear incident wave under the linear incident wave, not the actually incident plus diffraction all other thing. No, it is only simply under the incident wave. Now, you know that eta is or is we define is a cos k x minus omega t, right. This is how we define the eta. Now, if you look at the vector sense, now here that eta is nothing but your wave elevation, right. So, if I take a this the wave, so this wave elevation or the z is defined by this formula, right. So, I just modify it as a z equal to, now a is nothing but a wave amplitude a, and in now the cos, if I write in vectorial sense, like if you have this suppose that there is a heading angle, like this is the shape, let us see that this is the shape and it is having some kind of a heading angle, right. This is the beta. So, then you can know that this equation can be rewritten as it is k into x into cos beta plus k into y into sin beta and then minus omega t. In fact, to be specific, one should write omega e t whatever. So, this is how we are going to write the expression for z, right. Now, since it is going advance, so then the relationship between the fixed coordinated frame and the moving coordinate system. Now, this coordinate system is moving with the velocity u. So, definitely that x, which is the earth fix, and if x dash is the body fix, both are related by this equation x dash plus x equal to x dash plus u t, fine. And since it is going, there is no movement, linear movement in the y direction. So, y definitely equal to y dash. So, this is actually my the whole picture. Okay. Now, you see there is a 5 picture 1, 2, 3, 4, 5. Now, what is this picture? So, you can read out here, it says that in order to find out the intersection, several cases may be arises depend on the number of the vertices above the free surface or below the free surface. So, we are actually dealing with these 5 cases. Now, this is not general, like you can see that 1, 2, 3, 4, 5, these are the panels, right, and we have considered that this panel could be either triangular or quadrilateral, right. However, in general there is not such restriction on the vertices, it could be hexadecimal also. However, in our code, in that panel method, we use either it is a triangular or it is a quadrilateral. Now, you can see here that there is a 5 possibilities. Now, this black line is nothing but the, let us say, exact weighted surface. Now, this is the exact weighted surface and you are here, like this is your panel. Now, this panel, like further you can do to make it more clear, we can further split into this way. Now, you can see there are 3 type of panels, right. Now, if you look at here carefully, then you can see that there is this panel is completely outside the water, and also you can see there are this panel, it is completely inside the water. So, therefore, this sort of panel actually I am really not going to look at. Now, for me the interesting panels are these panels, this one, that some part you can see that inside the water and some part is outside the water. Here also you can see some part is the inside the water, some part is the outside the water. Here also some part is inside the water and some part is outside the water. Here also you can see the same. So, when you do this algorithm, that first thing you need to look at is basically what are the panel that you are getting, that some part is below the water of the panel, some part is the above the free surface. So, we need to consider only this sort of panels. Now, if you think of that what type of panel I mean like arrangement could be like this. Now, you see here there are lot of case can be arise. For example, you can see the picture number 1, it is a quadrilateral panel. Now, if now this black line is basically that the free surface is passing through, and then you can see that it is this is still actually a quadrilateral panel. Now, look at the second picture, it is a quadrilateral panel. Now, however, when it passes through it becomes a pentagon. Now, here is a quadrilateral panel, after this you can see it is a triangular. This is this one is a triangular panel, but after if you consider the free surface it become a quadrilateral. Now, here you can see it is a triangular panel, after it split it is again a triangle. Now, here we consider this is the 5 cases that we can see when a free surface is passing through a panel, there is not more other type of thing. However, if there is a bad paneling, for example, you have a this sort of panel, okay, and still it is possible that your actually the free surface can be go through like this way. See, it is a very complicated a paneling. So, we avoid such panels, right. We really do not want this sort of panel. It is a quadrilateral panel of course, but it is a very bad quadrilateral panel, and this becomes extremely complicated situation. So, at the initial stage when you do the paneling or meshing, you should avoid such kind of panels, right. Okay. Now, here there are 2 different approach one could take. Now, first one is the determine the point on the free surface for a panel using the binary search, or considering the free surface as a Nernst surface and directly use the surface splitting techniques, like there are if you use very commercial softwares, maybe directly you can find out such type of functions which actually the split the surface to Nernst surface. For example, if you consider the ship, now if you do the body plan, now this one is a curved surface, this one is curved surface, and also you can see this is also a curved surface. Now, maybe there are certain functions available in some commercial code, where actually you can the split is possible of splitting to Nernst surface, and find out the intersections points. This is possible. So, but let us not discuss this part. This one is much more realistic and one could able to write down this one. Now, before we go into this the binary search method, let us try to find out there is another easy way to calculate or capture the free surface. It is not that accurate, but it is very effective and as I said very realistic. We can call is a wet and dry panel method. Now, what is this? Now, suppose you have now I just draw this one a free surface and let me draw a two dimensional body over here. Okay. Now, let me do the paneling also. So, now here I am doing very fine mesh. I am making very fine panel, not very big panels. Okay. It only works if you make this panel very fine. So, now these panels are quite fine, very small, right. Now, you pick any panel, let us pick any panel. So, I just zoom this one, some panel like this you are picking up here. Now, what is happening here? You have this is your panel and then you can calculate the CG of the panel or centroid of the panel. So, centroid of the panel definitely has a coordinate some x, some y and some z. Now, at that point you try to calculate what is your wave elevation. Now, wave elevation is nothing but your z equal to eta. So, now this z equal to at this point the wave elevation gives you a cos k x into let us say cos beta plus k y into sin beta minus omega t. So, at particular time t. So, and now you put this x and y over here and you know what is your omega. If you put all this parameter you can get the eta or the z. Now, if you check is the z of centroid, I can call it z c, if it is more than the wave elevation z, then this panel I can call as a dry panel. And if I think that ZC the centroid is less than the Z that wave elevation, I can call that panel as wet panel. So, what is happening then in this case, I do not care like if it is let us say maybe it is go like this way just below, I can say that there is no contribution from this panel. Now, here let us say even if it is this like this, the free surface going, maybe that area is more, that area is less, but still since the centroid is below the free surface, I can call the wet panel and then I take the contribution of the whole panel. So, here I am really not discretizing the panel, I am taking the panel as it is. So, I take contribution from some panel and I do not take contribution of some other panel based on the criteria that if the z point of the wave elevation, that is z, the wave elevation is greater than the z point of the centroid. So, I can consider this as a wet panel, that means I take the contribution of whole panel even if that panel may not be like maybe that marginally as I said over here, like if this is the panel, this is the centroid and this just passed like this, still I can take the contribution of the whole panel. And maybe sometimes that may be like this is your centroid and it goes like this way. So, it is a significant amount is actually inside the water, but since that z point is above the wave elevation at that particular x y location, I simply discard this panel and I do not take the contribution of this panel. So, in a way this one is not I would say that very accurate, but if you do the very fine meshing, then actually more or less it will give very good result. Like if you want to avoid that complex mathematical analysis or algorithms, writing the complex code, splitting the panels, if you want to avoid it, you can simply you can do simplification of your code to capture the exact free surface. One can go ahead with this. Okay. So, now that how we determine the point on the free surface using the binary search. Now, it is written there is a minor work to find out which vertices of the panel are satisfied above the free surface and which lay below it. So, it is we call it a minor work, but it's yeah it is minor, but you have to do it very systematically to do that. I will come to that. Now, the panel vertices above the free surface you can mark with a positive signature, like the let us say plus, and the vertices below the below it you can mark with a negative signature. Now, if you use let us say the C++ or C sharp, then we have something called boolean, true or false. So, that can be used as a signature. If it is above the free surface you can take it is true, below the free surface you can take it is false. So, in that way actually, and if you use the Fortran, in Fortran also you can use true false by it is possible, but normally you can go with the integer 0 or 1, okay, or plus 1 or minus 1 whatever. Now, so then the thing is that you have to go from the positive signature to the negative signature. Now, let us demonstrate. Now, suppose you have a panel like this. Now, here I can say if this if all 4 are positive signature, let us say, so it means that it is either above the free surface or below the free surface based on that what you define with respect to the positive signature. Let us take if it is plus 1, then it is above free surface, if it is minus 1, it is below free surface. Now, if you get 4 plus 1, so it means that 4 point is above free surface. So, we are not yeah fine, no problem. And if the 4 point is below or negative, so it is entirely inside the what is called the free surface. So, here also we are not very much interested on these two type of thing. So, we are interested if the positive signature is either, for example, for quadrilateral panel, if the positive signature is 2 or positive signature is 3 or positive signature is 1. It means that 1 point above free surface remaining below, if it is positive signature is 1, you can get 1 1, it means that 1 point above free surface. You get 2 1 means 2 point above free surface. In this case, you can have 2 plus 1 and you have 2 minus 1, right. So, next one is very easy. Next one is you have to approach from the negative signature to the positive signature and you have to find out at which location actually it intersects. Definitely your free surface is intersecting here. So, you see that algorithm is not that difficult. I find out that 4 point, right. and then we see everybody has the 3 coordinate x 1, y 1, z 1. So, you have x 2, y 2, z 2, you have x 3, y 3, z 3, and you have x 4, y 4 and z 4. So, now as I said, the first point is very easy. Why? Because if you know your x 1 and y 1, you can find out at this point what is your wave elevation. Now, if the wave elevation is more than the z 1, so then this point you have negative signature, right, and at is this point, if it is more than that wave elevation z 1 point, so z 1 should have the positive signature. This is elementary. I know I have all 4 points, I have x coordinate, y coordinate, and then I know that at that point what is my wave elevation. If this wave elevation z 1 is wave elevation z is more than z 1. So, I know that this point having signature negative. If the z is less than, let us take z I some arbitrary, right. So, then I know that this z I is basically having the positive signature. So, this is elementary. Next point is that arrange, find out in a way you can get from negative signature to positive signature I must go, right. So, what I do now, you have this negative signature minus 1, you have this positive signature plus 1. So, I can write a straight line equation like this, where r is the parameter. So, I am writing in a parametric form, right. Now, if r equal to 0, you have the this point, let us take it is p 1 and let us take this point is let us say p 2, right. So, then if r is equal to 0, you have the point p 1, if r equal to 1, you have the point p 2. So, this is very elementary. Now, you start with r equal to 0.5, you will get some x y z. Now, you check that x y z is above free surface or below free surface, that is called binary search. Now, if it is above free surface, then in the next level, so you start with r equal to 0.5 and you take that this point maybe falls here. So, above free surface. Now, it is r equal to 0 and it is r equal to 0.5, then take r is equal to 0.25. Now, then you can find this point is below, then you divide this 0.25 to point. So, it is I think it is 0.375. Now, when you do the 0.375, then you can check that your z I minus z is less than epsilon, may be possible. At some point, if you do this continuing this process, so at some point definitely you are going to get some z values or some z values which is very close to that particular point. So, this is how actually you can find out your point on the free surface, and this is called the binary search. Okay. So, try it, write an algorithm and try to get this binary search. Now, once you get it, then actually we have to calculate the hydrostatic nonlinear pressure. Now, we have already discussed the hydrostatic approach. Now, if it is, if that point is that z is greater than 0, that means for example, that this is my the wave elevation and suppose this is my shape and this is let us say free surface. Now, if that z point is here, that panel z point is here. So, I am using the pressure at this point is this, okay. And if you think that this z point is coming over here when z less than 0, then we are going to use this pressure as this. Okay. So, this is how actually we are try to get the non-linear pressure, non-linear Froude-Kelloff pressure, and now when you integrate this non-linear Froude-Kelloff pressure, you will get the non-linear Froude-Kelloff force. Okay. That is what we are going, this is the discussion point today. So, let us stop today here, and in another 2 session we are going to discuss some kind of coding algorithm. It is very difficult to write a complete code of time domain parallel method at this moment, even in very elementary form also, but however, we can discuss some trick part, some critical coding aspect we discuss, okay, so that at least you could able to learn the basic functionality that is required to write the code. Okay. Now, before we stop, let us see, we have some kind of result with us. Let us see, we are taking this wiggly hull, and then actually now this is how it look like. Now, in wiggly hull, after z equal to 0, it is just go straight, okay, and this black one is the free surface. Now, we apply this algorithm. Now, we can see that it is very nicely, you can get the free surface, right. And once you get the free surface, that getting the pressure is really very elementary, right, using the hydrostatic approach. Okay. So, let us stop today. Thank you.